All right, back for part two. Now, what's strange about this trig identity stuff is some people will be quite good at this and will know the highway and stay on the highway and all that business, and other people will struggle. And really, the problem is there's no formula for this. It's a bunch of techniques we'll talk about, and I'll give you a few examples, but there are so many different things that you can be asked to do and prove, and so many ways to prove them that it can be a little bit frustrating. But what I want to do is show you some examples in the next couple of days and give you lots of time to work. And that's how you get good at these, by trying them and struggling and getting stuck and getting, off on the dark place and back on the highway. And of course, the flipped classroom with your classmates right next to you to read your proofs and to help you with your proofs is a great tool. All right, so on with the lesson here. An identity is an equation that's true for all values of the variables. It says almost all, and the almost all comes from this sort of thing, right? If we know that this is an identity from last year, right? So this is true for all values of x, except, if x gives you a 0 on the bottom here, except when cos x equals 0, then it's not true, right? The function's not defined. So the functions involved aren't defined. And so we got to be aware of that, except when the functions, the functions involved are not defined. So sometimes tan x isn't defined. Well, obviously this wouldn't be true if tan x isn't defined. And that's true for all of our values. But for any other value of x, this is an identity. It's true. Note, one counterexample is enough to show an equation is not an identity. So say you've got a left side, right side. If I could find some value of x, any value of x that made this not true, then there's no way it can be an identity. So proving is this left side, right side. If you're trying to prove that it's not an identity, it's actually easier, because as soon as I find one example where it doesn't work, then I know it's not an identity. So keep that in the back of your brain. For the most part today, we're going to be asked to prove stuff that are true, so we'll know that it's always true. So here's an example that we're asked to prove, so this must be true. There must be a way to turn the left side into the right side, and we're going to do this in just a second. How do we set up? And this big, by the way, the big gray rectangle here has got my strategies. And which one do we use? Well, we don't know. That takes practice. That takes practice and practice and practice. And some people will do it differently. Certainly, the first thing we do is we split the left side into the right and the right side. So the left side is cos 2a, and the right side is 2 cos squared a minus 1. And somehow I want to turn the left side into the right side. And so what's some general techniques? So, some general techniques. We do the left side and the right side separately, use known identities and substitute. So one thing that we might want to do is we know a formula for cos 2a. Well, what is it? Do you remember? Well, if you don't remember, you need to have that sheet. And I think there's my sheet. And no, you can't have a copy of this. I suppose you could screenshot this and print it off, but it's better if you make your own copy. And look, right there is a formula for cos 2a. So I'm going to apply that formula. Right? I'm going to write cos 2a minus sine 2a. This is a version of the cos minus sine, right? And already, because I'm looking back and forth, I know to stop when the left side and the right side are equal. Already it looks better, because I got cos squared a and I got a cos squared a there, and there's other stuff going on that I'm not sure of. I've got to keep going. So how do I know what to do, how to continue? Well, here's some other techniques, okay? So here are some strategies. in general, one of the things we might want to do is write in terms of cosine sine. So if we have a tangent, or if we have uh, reciprocals like cosecant or secant or cotangent, that we'll want to write those in terms of cosine sine. That's a good strategy. We might want to expand. In fact, that's the strategy we used back here, right? We just expanded the left side and all was good after that. We might want to factor. You know, this kind of looks like a factor. We might want to try and factor that. We might collect like terms. We might get a common denominator. We might multiply by a convenient form of 1. All of these are strategies, right? The idea is we have to develop our tools and instincts to know what to do when. Okay? And people's proofs will look different. As long as I can somehow turn the left side into the right side, I've got my own proof. One thing I might be thinking here for this one, because I'm back to this one. These are the techniques that we're going to come back to again and again. I'm going to get rid of this so I have some time. In the margin here, I can do some extra work. How am I going to use this? Well, this squared business is ringing a bell. This kind of looks like this, right? The good old Pythagorean identity from grade 11, I might be able to use this. And notice, I've got cos squared a's and sine squared a's all over the place. I also have a 1 here. Maybe I'd want to substitute for 1. Does it matter what I substitute for? No, but let's try something, all right? Let's try something. I'm going to, because this looks okay here, and this is a formula, I'm going to isolate cos squared a, right? And then I'm going to put it in here. Why am I choosing that? Well, I'm choosing that just because it seems like a good thing to do. It seems like it might be on the highway. So I'm going to isolate cos squared a in this formula. Notice this is in the margin. Or you could think of just doing this in your head. And so where I have this square, I'm going to put this formula. So in here, I'm substituting. I'm substituting in here 1 minus sine squared a. Everywhere else is still, there's the 2 and there's a minus 1. And now notice I've got some algebra to do. I've got some expanding and maybe some collecting like terms to do. And let's see where this goes. 2 and then minus 2 sine squared a minus 1 equals, and then I can collect some like terms here, 1 minus 2 sine squared a. Did that work? No, that didn't work. So the left side isn't equal to the right side. So what am I going to do? Well, hang on. I've got an expression that has just sine squareds in there. Maybe I'll try that over here. Maybe I'll try and make the same substitution over here, and maybe something good will happen. Let's try that. Let's try the same substitution over here. So where I have cos squared a, I'm going to put 1 minus sine squared a. The rest of this side I'm going to copy down. And what happens? And what happens is some goodness, right? This brackets, I don't need to expand. 1, and then I have a minus sine squared a and another minus sine squared a. And then now, look it. I have the left side equal to the right side, and the identity holds. Could have I done it some other way and not had to make 2 substitutions but only 1? Oh yeah, probably for sure. In fact, if I would have substituted for sine squared a straight off, then I could have got both sides only in terms of cos squared a, and I would have had my formula. Notice that this one here is one of the other versions of the cos 2a formulas that we can actually use now. So this is so common that we're actually going to add this to our list of known identities. And in fact, this one that we came across in our proof, we're also going to use. So maybe you noticed this when I went to my list of known identities, that those two were actually on my list. Okay, and so these ones are common enough that we can use them. And in fact, it's true that once we prove something is an identity, we can use them to prove more stuff. And in fact, that's what the last 3 days of class has been about, is about proving these basic facts here so we can prove our own identities. All right, well, let's keep going. We got a couple more examples, and I'm going to start picking up the pace, okay? Let me just put this one aside so I have some room. Oops, maybe I can't. That's okay. What do we got? Left side is a mess. Right side is not as much of a mess, but it's a cosecant x. And this side is, I'm just copying it down. How am I going to do this? And I need to build up some instincts. First of all, one of the strategies was to write things in terms of sines and coses, right? Write things in terms of sines and coses. That's a good start. So cosecant, for instance, is 1 over sine x. That's that one reciprocal identity. And notice this side is pretty simple. There's, I can't do much else with it. So it's probably the right-hand side that I'm going to be working with for the most part. And I'm going to try the same strategy. I'm going to write all this stuff in terms of sines and coses. So secant is 1 over cos x. Tan x is sine x over cos x. And see, when I see something like fractions over fractions, I get just a little bit worried. Here. But let's try something. And notice that it might be your instinct now to get a common denominator and collect like terms. That's fine. You could. Notice one thing we could do, and this might tidy things up a little bit, is this idea of a convenient form of 1. If I multiply by, I'm going to change colors, if I multiply by cos x over cos x, notice that that will get rid of the denominator on the top, and it'll get rid of the denominator on the bottom. So if I multiply by the convenient form of 1 of cos x over cos x, what do I get? And this might not be your instinct. Your instinct might have been to get a common denominator, and by the way, that works perfectly fine in this case. But I'm going to continue this way just because I wanted to show an example of this convenient form of 1 business. Cos x times 1 is cos x. This is cos x divided by cos x, which is just 1. And what do I got here? I multiply here. This is sine x over cos x times cos x is just going to be sine x. The cos x cancel out, and then I'm left with sine x times cos x, which doesn't look great, but a little bit better. Have a peek over at the right-hand side. 1 over sine x. So somehow, this has got to go. This thing has got to be a 1, right? This thing here has got to be canceled out somehow. And if I look at the bottom, I got a common factor. I got a common factor of sine x. So now the strategy is more algebra stuff. Try and common factor. So on the top, I'm just going to leave cos x plus 1 on the top. But on the bottom, I'm going to take out a common factor of sine x. And what am I left with? 1, because I divide sine x by sine x, I get 1. Take out the sine x there, and I'm left with cos x. Now look, cos x plus 1, 1 plus cos x, those are the same thing. And then I can cancel that common factor, and I get 1 over sine x, and I got it. Left side equals right side, and the identity holds. Now, I know I'm getting deep into this video, 14 minutes, and this one looks awful. Look at this. This is one of our we got 2 double angle formulas. There's stuff all over the place. It looks like a mess. This one's actually not bad. Okay, it'll be less than a couple minutes, as we'll see. I'm going to copy this and maybe put it on a new page just so I have some room. I'm going to use the same strategy, though. I start with left side and right side, a line down the middle, notice my left-hand side this time is already in terms of coses and just coses and sines, well, just coses in this case. So this might give me the idea maybe I'm working with the right-hand side in this case. Well, what do I got? I've got two of my compound angle formulas, cos, cos minus sine, sine here, cos, cos minus sine, sine. That's that one, right? That's that one. And then this plus sine I write down. And what's the cos of x minus y? Well, if you don't remember it, you can look it up on your formula sheet for right now, but it's cos x cos y plus sine x sine y. Well, how does that help us? It's starting to look bad again. Am I on the dark path? No. This is actually pretty nice. This is beautiful, actually, because look, negative sine x, positive sine x, cancel, cancel. These are like terms. Cos xy and cos xy equals 2 cos x cos y, and wow, that one was easy peasy, actually, right? This compound angle formula, as long as I know what to substitute, right? As long as I knew that this was true, right? These formulas, cos y minus sine sine, this was an easy one, right? And I knew this one too, right? I knew those. This was an easy proof. And in fact, you'll see that the ones that are based on, and by the way, this one back here, this was all grade 11. There was no new formulas for us this year. This was a grade 11 one. This one, a grade 12 one with compound angle formulas, not as bad. Left side equals right side. The identity holds. Okay, that's it for today. I'm going to show you a couple more tomorrow, but the idea is, you know, and I've only assigning 4. This is like get going on them, try some, and then the next day you can, if you get time, you maybe start on the next day's stuff. I'll show you a couple more tomorrow, but the whole idea, I can't show you them all, right? There's too many things that you might be asked to prove, but prove them, okay? Get stuck, get back on the path, keep at it, folks. Good luck with the Trig identities.